Let's go in and decompose the difference between different types of ciphers. One is a block cipher, and the other one is a stream cipher. And it really is makes sense, I think, after we go in and take a look at it. I hate defining the definition with the definition, but for this particular case, I'm not going to use the word block. I'm going to use the word chunk. So we take a chunk of data and we encrypt the chunk of data. You know, if you think just 8 bits are a byte, if we were to take a byte, that would be a chunk of data. And so that's a block. And in that particular case, if you think about like a butcher cutting up meat, they would cut it up into big chunks of meat. Whereas the stream cipher is individual characters. So I oftentimes think about water and stream, and this is supposed to be a spigot, where there's little drops that each little drop is an individual character. So it's a leaky spigot. Maybe we need to call a plumber. And so that particular case, each individual character in the stream cipher would allow us to encrypt that. And so the idea here is that depending on whatever you're using, so in the case of the block, usually you would have the same input use would generate the same output size for these. And so that's this diagram over here on the right-hand side. In addition to that, what we can look at are these different types of algorithms for symmetric keys. So for every communication that we have, for each communication that we have, there's going to be 2 symmetric keys. There's going to be one that's going this way, and then another one that's going this way. And why is that? Well, that is because that same key pair are used for the parties and in a way that is for a secure communications channel. Another way to look at this is this right here. So depending on the number of keys that you have, in this particular case, if there's just 2 people in our symmetric realm of trust, then there would just need to be 1 key. If there are 4 people in this scenario right here, there would need to be 12 keys. If this is the first time you're seeing it, how do we do that? Well, the number of users is n, and then we take n minus 1 divided by 2, and that is the formula for getting the number of keys for symmetric encryption. So in this particular case, each person would need to have, it's almost like a mesh network. Each person would need to have different ways that they would communicate to each other. So one over here, person 1 would need to have a key for 2, a key for 3, a key for 4. Person 2 would need to have a key for 1, a key for 2, and a key for 3, a key for 4. Person number 3 would need to have a key for 1, a key for 2, a key for 4, not themselves, right? And then person 4 would need to have a key for 1, a key for 2, and a key for 4 or for 3. In this particular case, that would give us 3 for each, 3 keys for each. This is getting kind of messy, I know. 3 times 4 would give us 12. And so if we say there's 4 users, right, just to do this math, 4 times 3 is 12 divided by 2. We would need 6 overall. Well, how does that work right there, right? So let's jump into these historical ciphers. And so these two-way functions, we mentioned this before. I'm not going to jump back into it, but essentially encryption and decryption, and there's got to be some sort of algorithm and key in the middle for us to be able to do it. And there's different types, and again, this is classical cryptography, so substitution cipher and transposition cipher. There's the Caesar, the Wegener, and Playfair, as well as some other ones. And then there's also, just ways that we can replace the values to try to substitute in a way that's meaningful. Transposition is to literally move the position from one to another, or rearrange it in a way that is meaningful. But you have to remember, in this particular case here, I have some transposition ciphers down here at the bottom. Here's attack at dawn, and if we were to utilize the positioning of this, the plain text message, and just move them around into different positions, kind of like you're taking cards on the table and kind of shuffling them, as long as you remember the original position, right? So 1 is here, 2 is here, 3 is here, 4 is here, 6, and so on and so forth. You can reassemble those scrambling based on this transposition, the number values. So these are message counters that we put onto this message to help us put it back to a decrypted value. And so with transposition, really we're just rearranging in a way that's meaningful. It's kind of cool. In addition to that, we talked about this thing called the Caesar cipher before, and this is one that you have to really ask. Did Julius Caesar really create this, or did one of his Longbeards that was working for him, create it, and then Caesar said, "Great idea. I think I'll take that for myself." And so, the way that this works is that the alphabet, if you just take a look at the alphabet here, and this is a rot 0, which means that we're not rotating it any here. This is just the true alphabet that we know, right? If you rotate it 1 here, put Z first, and we rotate everything else 1 value or 1 character to the right, that's the rot 1. Right. Rot 2 would be 2 values. Rot 3 then. So the original Caesar cipher was this one right here down at the bottom, the rot 3. All right. So you should see on the screen the Wegener cipher, and I'm butchering the name. I'm not French or whatever nationality this guy was, but essentially they come up with this, what they call the polyalphabetic cipher. And the word poly meaning many, and alphabetic means obviously the alphabet. So having many alphabets represented, and it's a slight shift with each one of them. So if you can look at it, the plain text is this way, and then the key is this way. What's interesting here is if you just kind of think of it, you run to the right with the key cipher. So it's typically called a running key cipher. And so you have the key, you have the message, and then you end up putting those together in a way where you have the mod 26, because there's 26 different alphabets for this. And so you can calculate it in a way that's meaningful. So check it out. If we had the word secret as the plain text, and we had the word pickle as the key, what would that look like? Well, if we take S and we take P, we bring them together, what do we got? Bippity boppity boo. We got H. P and S would equal H, E and I would equal M, and you can actually do this on your own time. So that's the Visionaire cipher. This is something that I really enjoy, and you may as well. There was this guy who was a math guy, and his name was Gilbert Vernum, and he created what he called heaven forbid that he called what he called the perfect type of secrecy. I mean, how dare him be so confident in his algorithm? And think about the timing of this right here. 1917, 1918 time frame. There were so many great mathematicians around historically in that time. Homeboy came out and said, I've created what I think is the perfect type of secrecy. And so, the idea of the Kirchhoff's principle, which if you recall, it says, hey, if you think that your stuff don't stink, share it with the rest of the world. So Burnham was like, okay, I'll share it with the rest of the world. And so what he did is he created this this thing that was called the one-time pat. And here we are 107 years later, and we're still using this on a daily basis. The one-time pad and the one-time password. So think about this. The idea or the notion of it is that, it can only be used one time. The problem, that is also a problem, because it can only be used one time. And how do we get that to people, right? How do we get that to people? So just by a show of hands here, how many of you have today already used OTP? If you haven't used one-time passwords today, it's likely that you're going to use it when you go home and play your video games tonight, or log into your Google account or whatever. And the idea is that it's only good once, and it gives us what Gilbert Vernum called the perfect type of secrecy, unbreakable cryptographic system. Now, there has been times where, for instance, with RSA, the secure ID tokens, like the key fobs that they had. This was back in probably 2016, 2017 timeframe. Somebody could look it up. The root key for that RSA key fob was compromised. And so what RSA had to do is they had to reissue all of the key fobs out to people. The company RSA I'm talking about. It was huge and they lost a lot of money off of that, Brian. They lost a lot of money off of that. But yeah, so this one-time pad, one-time password, still used today, in practice, and something that typically you see quite a bit of.